Now, because we already spent some time with these already, I'm just going to breeze through them quickly and then get to the categorical syllogisms, which we did not start yet. Now, the author begins chapter 2 with those basic structures of propositional logic. Now, the reason why we call it propositional logic is because each one of those statements is called a proposition, and in some cases, propositions are somewhat complex. And the main unit of discourse in propositional logic is a statement or a proposition. Now, those structures that we've already seen so far are examples of so-called, or as it's called, propositional logic. We'll run through them quickly. Modus ponens, you'll recall, looks like this. If it's the case that P, then it's the case that Q. It is the case that P, therefore Q. If this thing wire is copper, then it conducts electricity. It is indeed copper wire, therefore this wire will conduct electricity. As long as you put in true premises, a true conclusion will spit out. Now, even though this happens a few pages in, I want to introduce you to a formally fallacious form of argument. What's a formal fallacy? We call them formal fallacies because why? There's some, what's that?
They're wrong.
Yeah, there's something structurally wrong with it. There is something wrong with the structure that makes it such that the conclusion does not necessarily follow from the premises. Now, the formal fallacy that looks a lot like modus ponens looks like this. If P, then Q, it's the case that Q, therefore P. This is a fallacious form. The reason why I mention it is because on some homeworks I've already reviewed ahead of time, this mistake was made in a few cases. This is a fallacious form that we call affirming the consequent. Now, if the author did not make it clear as to why it's called affirming the consequent, it is because this statement right here, if P then Q, we call this I'll write it big. Statements that are structured like this are called, it starts with a C.
Conditional.
Thank you. It's what we call a conditional statement. Unsurprisingly, it's called a conditional because it means something like this. On condition that this is the case, this will also be the case. Now, this side of the conditional, the front end, we call this the antecedent. This tail end of the conditional, we call this the consequent. And if you want to remember that, if this is the case, this is consequently also the case. Now, the reason why we call this fallacy affirming the consequent is because we just did what in the second premise? Affirmed the consequent. Sorry if I stated the obvious. Sometimes the obvious is not obvious, so it pays to state it. Now, just to illustrate to you one reason why you can know that this one is invalid. is because if you plug in true premises, the conclusion will not necessarily what? Yeah, will not necessarily be true. If it's a wallaby, then it's a marsupial. But this animal is a marsupial. Well, can you conclude that just because it's a marsupial, it's also a what? A wallaby? No. There are many other kinds of animals that are marsupials. The same way if I said, if this is copper wire, then it will conduct electricity. This here wire conducts electricity. Therefore it's copper. No, there are other things that conduct electricity. Now this is where in the chapter the author draws the distinction between sufficient conditions versus necessary conditions. Now admittedly it sounds really, really sophisticated, but it's really what? It's really not. It's just fancy terminology. We say that something's being copper wire is sufficient for its conducting electricity, but it's not what? It's not necessary. This is because other things conduct electricity too. Now, its conducting electricity is a necessary condition for its being copper wire. Because why? All copper wire conducts electricity. It is an essential attribute of copper wire. Just like being a marsupial is something built into the very concept of being a wallaby. Now, I could get out diagrams to illustrate this, but we'll have time for diagrams later on. Actually, maybe I will. How many of you guys remember doing these diagrams that talk about sets and subsets? You may have seen Venn diagrams, you may have seen Euler diagrams. If you're having bad flashbacks, I do apologize. The thing is, they're really not difficult if you give them a chance. And if they're things that don't click for you automatically, it helps to be walked through very slowly and sometimes repetitively. Now, suppose that this circle right here represents all things marsupials. What is everything outside of that circle? Non-marsupials. Everything outside of this circle is non-marsupial. Now, wallabies are in here. Wombats are in here. Kangaroos. Platypus, are they in here too?
No.
They're not?
No.
There's some other funky thing. I guess koalas are in here. Yeah. Or do they don't count either? Oh.
That's the qualification for marsupial.
Oh, yeah. All right. Wrong again. All right. Now, if I say, if this thing is a wombat, therefore it's a marsupial. Well, that can clearly be shown once we've demonstrated what the relationship is here. Now, if I say it's a marsupial, you can't therefore conclude that it's any one of these. Because all of those things are sets within the set. Now, I'm going to leave this up here for a minute. You've seen modus tollens before. I've shown it to you more than once. Modus tollens looks like this. If P then Q, but not Q, remember that's the symbol for not, therefore not P. If it's copper wire, then it conducts electricity. But this doesn't conduct electricity. Ergo, this cannot be copper wire. If it's a wombat, then it's a marsupial. But this is not a marsupial. Ergo, not a wombat. This is a valid structure. As long as you plug in true premises, you'll get a true conclusion. Now, the related fallacious form any guess what this fallacious form is called? Denying the antecedent. I forget what page number it's in the book. It's in my notes, though, too. This one's a fallacious form. If it's a wombat, then it's a marsupial. But this is not a wombat. I can't conclude, therefore, it's not a marsupial. Because there's other things in the class of things marsupial. Now, the reason why this structure does not work out is because it does not make the necessary connections to draw this conclusion. Because of the one-way direction of the conditional. Remember, the conditional says if P then Q. It doesn't say what? It doesn't say if Q then P. The relationship between this and this is one directional. This is a sufficient condition for this being this. Is that pretty clear, I hope? Do note that denying the antecedent and affirming the consequent are arguments that people frequently mistake for valid arguments. Even though all you have to do is plug in, very clear data, and you can usually, you can easily show that it's not a valid form. Because why? If it's valid and its premises are true, its conclusion will always be true. Next. Two more. You've already seen the hypothetical syllogism, which looks like this. If P then Q, and if Q then R, we can therefore conclude if P then R. Of course, you can plug in your wallabies and marsupials and so forth, and you can clearly see some very simple examples. If it's a wallaby, then it's a marsupial, and if it's a marsupial, then it's a mammal. Obviously, if it's a wallaby, it's also a mammal. We've got mammal here. Marsupial is a subset of that, and of course, wallaby is a subset of that. That's just a simple way of illustrating why it works. And by the way, deductive logic is all about relating concepts to one another. And if it feels mathy, there's a reason why it feels mathy. And it's because mathematics is all about what, too?
Deductive reasoning.
Yeah, it is a deductive system, and it's all about relating things to one another, except instead of logical concepts, you're relating numbers to one another. You're relating numbers to one another. But yeah, this is a Yeah, this is a deductive system. Mathematics is a deductive system too. And this is why we can kind of use the same kinds of diagrams to illustrate the relationships. How many of you did Venn diagrams elsewhere? Good, a few of you. We're going to see some easy ones shortly in here. And if you haven't done them before, no worries, because I step very how? Yeah, I step very slowly, and I'm open to asking questions. I don't race through it. If somebody has a question, please stop me. John Venn was a what? Logician and mathematician. That guy Euler diagrams I mentioned, mathematician. Yeah, a lot of the rudiments of deductive reasoning come out of mathematical reasoning. They are parallel. This is why some colleges actually allow you to take logic courses as your what? Yeah, as your math/critical thinking component. As your math/critical thinking component. And by the way, people who consider themselves not to be very good at math sometimes can master logic fairly easily. And I think part of it is because here at least we're starting with what? Words. And for some people, words just feel more conceptually comforting than numbers. I know some people have math anxiety, and some people have probably been taught to have math anxiety, which is not a good thing. But yeah, anyway, I'll behave it a little bit. Disjunctive syllogism looks like this. This word disjunct is referring to the either-or relationship. If it's the case that P, or no, it's the case that P, or it's the case that Q. This little symbol right here is the one that logicians use to stand in for the or relationship. It's P or it's Q. But it's not P. Therefore, it's got to be Q. John Quincy Adams was either the 6th President of the United States or he was the 7th. He wasn't the 7th, therefore he was the 6th. This argument is valid. It's also what? Untrue. No, this one's sound, because he was the 6th. Yeah. I didn't put in the wrong numbers this time. The last time I did that intentionally. Now, a couple other things that are not in the book, just I want to show you, because it might help you to see these relations better. I won't be doing this to you on a quiz because the author doesn't do it in the book. But in propositional logical symbolization, one of our other connectors we affectionately call the dot. The dot stands in for the logical relationship and. It's also known as conjunction. Guess what conjunction means in propositional logic? Easy answer is? Yeah, it means the same darn thing as it does in everyday language. It means the same darn thing as what you learned in a 5th grade grammar class. If I make the statement P and Q, what that means is if this statement is true, both sides of the and have to be what? Both sides have to be true in order for that to be a true statement. Now, folks, if this is a true statement, guess what I can deduce? if this statement P and Q is a true statement, can you guess what else I can deduce?
Q and B.
Yes! I can deduce P on its own. I can also deduce Q on its own. Because if this total thing is true, then both sides of it have to be true. This is actually a propositional logical rule of inference called simplification. This is a deductive rule called simplification. Because if both of these are true, each one can also be called true independently. Let me give you another odd one. Suppose that it's the case that P is true. I can also make this statement, and this just might sound totally bizarre. If P is true, I can say P or Q without respect to the truth value of Q. In other words, if I know that P is true, I can say P or Q, no matter what Q is. It is January 2018 in the year of our Lord, or I am the king of Siam. I mean, I can literally put in any kind of inanity as Q, and this would still be a true statement. Because for an or statement to be true, all you need is what? Only one side needs to be true in order for this entire statement to be true. This is a rule that we call addition. This is a rule that we call addition. Now, I'm almost out of time. 10 minutes. I want to introduce you to